Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back to the show. We are doing something a little different today. Usually when we sit down to talk about the bleeding edge of astrophysics, when we try to visualize what it looks like to study worlds that are hundreds of light years away, we all have a very specific, almost Hollywood-style image in our heads.
Oh, absolutely. It's the Cape Canaveral aesthetic, isn't it?
Totally.
We picture these massive vertical integration buildings, clouds of steam, the whole countdown clock thing, and millions of pounds of thrust just fighting gravity.
Exactly. It's loud, it's fast, and it involves billions of dollars of titanium and composites hurling themselves into the vacuum of space.
It's drama, pure raw power.
Right. And so we have this conditioned bias that space science equals rockets. We just assume that to get high-quality data, you need high velocity and extreme altitude.
You need to escape Earth entirely. That's the assumption.
But the documentation we're looking at today, specifically a fascinating report from Universe Today and phys.org about a mission called ExoPlanet, it completely dismantles that assumption.
It really does. It's a wonderful reminder that sometimes the most sophisticated solution to a really high-tech problem isn't about going faster or higher or, just using more brute force.
It's about being smarter.
It's about being smarter with where you put your instruments. It's about finding the clever workaround.
Right, because the vehicle at the center of our conversation today isn't a rocket.
Not at all.
It doesn't have thrusters. It doesn't have a heat shield. It's a balloon.
A balloon. And it's a balloon that, if everything goes according to plan, is going to tell us more about the weather on alien planets than perhaps any rocket-based telescope currently in operation. We are talking about the ExoPlanet mission.
Let's break down that acronym before we get into the physics, because it sounds intense. ExoPlanet.
It does sound pretty energetic. It stands for the Exoplanet Climate Infrared Telescope.
Okay.
And while the name suggests all this high energy and excitement, the actual method of deployment is remarkably gentle. It's almost floaty.
Floaty. I like that. So the plan is to float a telescope to the very edge of the Earth's atmosphere.
Exactly. And just have it sit there to stare uninterrupted at a very specific type of alien world.
Okay, let's establish the scale here. When we say float a telescope, are we talking about something like a weather balloon you'd see on the local news? Or is this more like the Red Bull Stratos jump? How high are we actually going?
We are definitely talking stratospheric. Think much, much bigger than a standard weather balloon. The mission profile calls for an altitude of 40 kilometers.
40 kilometers?
Yep. And to put that in imperial units, for those of us who think that way, that's roughly 25 miles straight up.
25 miles. Okay, can you contextualize that for me? If I'm looking out the window of a 747 on a transatlantic flight, how far above me is this balloon?
Right, so a commercial jet cruises at, between 30,000, 40,000 feet?
Something like that, yeah.
So that's roughly 10 to 12 kilometers up. This balloon is going 4 times higher than a commercial flight.
4 times higher.
If you were in that jet looking up, the balloon would still be just a tiny dot in the black sky above you. It's not in the blue part of the sky anymore. It is cruising the upper stratosphere.
But, and this is a really important distinction we need to make, it's not technically space, is it? The Kármán line, which is sort of the international welcome to space sign, that's at 100 kilometers.
Correct. It is not technically outer space. You are still within the influence of Earth's atmosphere, thin as it is up there. But here's the thing. For the specific scientific problem they're trying to solve, 40 kilometers is the magic number.
The sweet spot.
It's the absolute sweet spot where you get, something like 99% of the benefits of being in space, but without the, billion-dollar price tag of a rocket launch.
I want to really dig into that magic number concept, because that really seems to be the linchpin of this whole project's economic and scientific argument. But first, what exactly is ExoPlanet looking at? You mentioned alien weather.
Yes. The target is a very specific, very dramatic class of planets known as hot Jupiters.
Hot Jupiters. It's a vivid name. It implies a lot.
It does, and it's quite literal, actually. These are gas giants. So planets with the mass and composition roughly similar to our own Jupiter, but they are not sitting out in the cold suburbs of their solar systems like our Jupiter is.
Right, Jupiter's way out there.
These guys orbit incredibly close to their parent stars.
How close are we talking? I mean, Mercury is close to our sun. Is it like that?
Oh, much, much closer. So close that a year, one full orbit around their star might only last 2 or 3 Earth days.
2 or 3 days. That is incredibly fast. So they are just speed running their orbit.
They are. They're absolutely whipping around their stars. And because they are that close, they are just roasting.
I can imagine.
Temperatures on the star-facing side can reach thousands of degrees. We are talking about worlds that are essentially glowing with their own heat, where the atmosphere is being constantly blasted by stellar radiation.
So we have these massive, scorching, fast-moving planets. And Excite is designed to map the climate of these hellscapes.
That's a good word for them, exactly. But to do that, you immediately run into a massive obstacle in observational astronomy. To see the heat signature of a planet, you need to observe in the infrared part of the spectrum.
Infrared, that's heat radiation, right?
Right. Our eyes see visible light. But if you want to see temperature, if you want to see the thermal glow of a hot planet against the cold darkness of space, you have to look in infrared. It's the only way.
Okay, so what's the problem with that?
The problem is Earth's atmosphere absolutely hates infrared light.
Hates it in what way?
It absorbs it, specifically the water vapor in our atmosphere. You can think about humidity. Water molecules are incredibly good at absorbing infrared energy. It's the greenhouse effect, basically.
Okay.
So if you put an infrared telescope on the ground, even on a super high mountain in Hawaii or the Atacama Desert in Chile where the air is really thin, you are still looking through this thick, soupy blanket of water vapor.
So the signal from the planet just gets lost in the noise of our own atmosphere.
It's worse than noise. It's a total blockage at certain wavelengths. It's like trying to look at the stars on a foggy night or trying to see through a steamy window. The signal just doesn't get through.
And this is where the balloon comes in.
This is where the balloon is the hero.
Back to the 40-kilometer figure.
Right. Because if you can get a telescope up to 40 kilometers, you are physically above 99.5% of the Earth's atmosphere. More importantly, you're above almost all of the water vapor.
So suddenly the fog clears. The steamy window becomes transparent.
Precisely. The sky becomes crystal clear in the infrared frequencies they need to see. For the purpose of this specific telescope and this specific science, 40 kilometers is space. The photons from that distant planet can travel all that way and then hit the detector without bumping into any pesky water molecules in our atmosphere at the last second.
That is a fascinatingly simple workaround. You don't need to leave Earth's gravity. You just need to get above the moisture.
And you save a fortune in fuel and hardware doing it. But there is another layer to this strategy, and it's a really clever one. It has to do with where they are planning on launching it.
Oh, right. You mentioned this.
For the main long-duration mission, they aren't just sending this up from Florida or New Mexico. The source material highlights a launch plan for Antarctica.
Antarctica. That seems, I mean, logistically, that sounds like a nightmare.
Yeah.
Why go to the bottom of the world to look up at the sky?
It does seem counterintuitive. There are 2 main reasons, and they're both brilliant. First, what are called the seeing conditions.
Seeing conditions.
It's an astronomy term for how clear and stable the atmosphere is. The air above Antarctica is very, very stable. It's incredibly cold, and crucially, it's the driest place on Earth. So you get even less of that residual water vapor.
So it's the best possible place on Earth to be, even before you go up.
Exactly. But the second reason, and this is the real game changer, is about time.
Time?
This brings us to a concept they call loitering. Think about it. If you launch a satellite into low Earth orbit, like the Hubble Space Telescope or the International Space Station, it is moving fast.
Unbelievably fast.
We're talking 17,000 miles per hour, something like that. It orbits the entire Earth every 90 minutes.
So from the satellite's perspective, the sun rises and sets every hour and a half.
Exactly. And more importantly, from its perspective, the Earth gets in the way. For roughly half of that orbit, about 45 minutes, the Earth itself is blocking your view of the stars you want to see.
You're in Earth's shadow.
You're in the shadow. You can't stare at anything for very long. It's a constant cycle of observation, then blockage. It's constantly blinking. Sun, shadow, sun, shadow.
I can see how that would be a huge problem if you're trying to, say, film a movie of a planet's weather system.
Yeah.
You'd have these massive gaps in the footage every 45 minutes.
Precisely. You'd lose all continuity. It would be a mess. But a balloon over Antarctica during the Antarctic summer?
The 24-hour daylight.
You got it. The sun never sets because of the Earth's axial tilt. It just circles the horizon.
So you never have to worry about the Earth getting in your way.
Not if you're looking outwards. If you point your telescope away from the sun, the stars are always accessible, 24/7. And because of the polar vortex winds, these stable circular winds that just go around and around the continent, the balloon just gently circles the pole.
It doesn't fly off towards Australia.
Nope. It just laps the continent. It loiters.
It loiters, and that lets it stare at a single target, one of these hot Jupiters, continuously for days on end. No blinking, no Earth getting in the way, just a pure, uninterrupted stream of data.
That is the whole ball game.
And that continuous stream is what allows them to get the very specific kind of data they are after. The report mentions something called phase curves. And I really want to spend some time here because the report makes it clear this isn't a side project. This is the core science of the mission.
Yes, this is the holy grail for this kind of science. It's what you can do with that loitering capability.
Okay, so let's unpack this. We usually hear about transits in exoplanet news.
Right.
That's how we find most of these planets, right?
Yeah.
The planet goes in front of the star, the light from the star dips a tiny bit, and we say, there's a planet there.
Correct. That is the transit method. It's fundamentally looking at a shadow, a silhouette. It's incredibly powerful. It tells you the size of the planet, how fast it orbits, and maybe, if you're lucky and the instrument is good enough, a little bit about the chemical makeup of the very edges of its atmosphere as the starlight filters through.
The edges. That's a key word.
A very key word. Then you also have what's called the secondary eclipse.
Which is the opposite.
The opposite. That's when the planet goes behind the star from our point of view.
Okay, so it disappears.
It disappears completely. And just before it vanishes, we're seeing the light from the star plus the light reflected and emitted from the planet's day side. Then it's gone. And we only see the star.
So you subtract the star-only light from the star plus planet light.
And the difference is the light from the planet's day side. That tells us how bright it is, how hot it is on that side facing the star. But both of those methods, transits and secondary eclipses, they're just snapshots. They are momentary events.
You see the front when it passes by, or you see the back before it hides.
Right. It's like trying to understand a marathon runner by taking a single photo of them at the starting line and a single photo of them at the finish line.
You miss the entire race.
You miss the whole race. You don't know how they handled the hills. You don't know what their pacing strategy was. You don't know if they struggled at mile 20. Phase curves are the video of the entire race.
So instead of just watching the planet cross the start or finish line, Excite watches the whole orbit.
It watches the planet go all the way around for days. And this is where the physics of hot Jupiters gets really, really cool. Because these planets are so close to their stars, they're subject to these massive gravitational forces that lead to a phenomenon called tidal locking.
We see this with our own moon, right?
Yeah.
We always see the same face of the moon.
Exactly the same principle. The immense gravity of the star has grabbed the planet and basically forced it to rotate at the exact same speed that it orbits.
So one side faces the star forever.
Eternal noon. And the other side faces deep space, forever eternal midnight.
That sounds incredibly extreme. One side must be boiling and the other must be, near absolute zero?
In theory, yes. If there were no atmosphere, the day side would be molten rock and metal, and the night side would be unimaginably cold. But here is the mystery. These planets do have atmospheres, and atmospheres move heat around, massive supersonic winds. So as we watch this tidally locked planet orbit its star from our vantage point here on Earth, we see different amounts of its day and night sides. We see different phases, just like the phases of our moon.
So we see the full night side, then a crescent of the day side appears.
Then it gets bigger. We see half and half. That's the Terminator line, the sunrise-sunset line. Then we see the full day side, and then it wanes back to a crescent and finally back to the night side again.
And by measuring the infrared light, the heat, during all of those different phases, we can build a map.
We are building a 3D temperature map of the entire world. We're not just getting one number for the day side and one for the night side. We can see the gradient. We can see how effectively the winds are dragging that immense heat from the day side around to the night side.
So if the night side is surprisingly warm, it means the winds are really efficient at circulating heat.
Exactly.
And if the night side is freezing cold, it means the winds aren't doing their job or the atmosphere is too thin to hold the heat.
Precisely. We are literally measuring the efficiency of the planetary heat engine. And we can get even more granular than that. This is the really wild part. On many of these hot Jupiters we've studied, we find that the hottest point on the planet isn't where you'd expect it to be.
Wait, how is that possible? If I stand directly under a heat lamp, the hottest spot is right on top of my head. That's just basic physics.
It is, unless there is a 5,000-mile-per-hour wind blowing across your head.
The wind.
If the wind is strong enough, it physically pushes the heated mass of air, it advects the heat, it shifts the hot spot away from the point directly under the star, usually to the east, in the direction of the planet's rotation.
So the hottest part of the day isn't noon, it's more like 3 p.m.
A very extreme version of that, yes. And by measuring exactly where that hot spot is located using the continuous phase curve, EXCITE can actually calculate the wind speeds and infer the atmospheric pressure on an alien world.
That is just incredible. We are effectively doing meteorology calculating wind speeds on a planet that's hundreds of light years away using a telescope hanging from a balloon floating over Antarctica.
It's a huge leap forward. It moves us from what some astronomers call stamp collecting, just finding planets and cataloging them, to characterization, which is actually understanding them as complex, dynamic, physical places.
Now, I have to play devil's advocate here for a minute, because whenever we talk about space telescopes, there is a giant $10 billion elephant in the room. We have the James Webb Space Telescope, JWST.
Yeah.
It is the most powerful, most expensive, most advanced observatory humanity has ever built. It's an infrared telescope. Why on earth do we need a balloon if we have Webb?
It's a great question, and it's one that the scientific community asks itself all the time. You would absolutely think the $10 billion telescope would win every single time. But ironically, Webb actually suffers from being too good for this specific job.
Too good. How can a telescope be too good? I don't understand that.
It's too sensitive. You have to remember what Webb was originally built for. Its primary design mission was to see the cosmic dawn.
The very first stars and galaxies.
The first galaxies born after the Big Bang. We're talking about objects that are incredibly far away, incredibly redshifted, and unbelievably faint.
So it's designed to see a single candle on the moon.
It's designed to see something even fainter than that. So what happens when you take that exquisite instrument and you point it at a relatively bright star in our local galactic neighborhood?
It's overwhelmed.
It's completely overwhelmed. It's like using military-grade night vision goggles to stare directly at a football stadium's floodlights.
You just see white. You get no information.
Exactly. The sensors saturate. The pixels on the detector fill up with electrons faster than the electronics can read them out. You just lose the data. Astronomers call it blowing out the image.
So the data is totally useless.
In many cases, for the brightest targets, yes. And this is especially true for the specific instrument mode on Webb. It's called PRISM. That is actually the best tool for this kind of continuous atmospheric study. Many of the stars that host these interesting hot Jupiters are relatively bright nearby stars in our galaxy. Webb literally cannot look at them in this mode without getting blinded.
So EXCITE is filling a really specific niche. It's designed to be less sensitive, which paradoxically allows it to look at the bright stuff that Webb can't.
It has a higher dynamic range. That's the technical term. It can handle the glare. And then, of course, there is the time and cost factor, which we just cannot ignore. Webb's observing time is arguably the most valuable single resource in all of astronomy.
I can imagine. The line to use it must be miles long.
The proposal acceptance rate is tiny, something like 1 in 10, maybe even less. So to go to the Time Allocation Committee and ask for 5 continuous days of Webb time to just stare at one planet.
That's a very hard sell.
It's an almost impossible sell, because in those 5 days, Webb could have looked at 100 distant galaxies, or analyzed the light from 10 different supernovae, or mapped a star-forming region.
There's an opportunity cost.
A massive opportunity cost. EXCITE is a specialist. It's a dedicated mission. It can afford to just sit there and stare at one target for a week or more because it isn't competing with the entire rest of the universe for its attention.
Okay, that makes sense for Webb. But what about Hubble? It's been up there for decades. It's certainly less sensitive than Webb. Can it do this kind of work?
Hubble has done some of this work, and it's been groundbreaking. But it runs smack into the orbit problem we mentioned earlier. It's in low Earth orbit.
Right, the blinking issue. In and out of shadow every 90 minutes.
Exactly. But there is a secondary, much more subtle issue that comes with that shadow. Temperature swings.
The telescope gets cold.
It gets cold, and then it gets hot again, over and over. When Hubble dips into Earth's shadow, it cools down significantly. When it pops back out into the direct, unfiltered sunlight of space, it heats up very quickly.
And that causes the structure to expand and contract.
Yes, thermal expansion and contraction. We all learn about it in high school physics with railroad tracks.
Sure.
But in a telescope that's trying to measure infinitesimal changes in light, Even a microscopic amount of expansion or contraction is a potential disaster. The whole structure sort of breathes.
Breathing. That sounds very ominous for a precision machine.
It creates noise and jitter in the data. The focus changes slightly. The alignment of the mirrors drifts. Every time Hubble comes out of the Earth's shadow, the scientists have to basically discard the first chunk of data from that orbit while the telescope settles and stops shivering from the temperature change.
So you get these unavoidable gaps in the data, even when you're not behind the Earth.
You get gaps and you get wobbles. It makes it incredibly difficult to stitch together a perfectly smooth, continuous phase curve. Excite, on the other hand, floating in the eternal gentle sunshine of the Antarctic summer, stays at a much, much more stable temperature. It doesn't shiver.
It all sounds like the perfect solution on paper. A stable platform above the water vapor, relatively low cost, with specialized sensors for the job. But paper is not reality. And the report does mention they actually took this whole thing for a test drive recently.
They did, and this is where the story gets really interesting from an engineering perspective. In August of 2024, they launched a test version from Fort Sumner, New Mexico.
New Mexico. Not Antarctica yet.
No, absolutely not. You don't go to the most logistically challenging and hostile continent on Earth for your first try.
That would be brave.
Or foolish. You do a shakedown cruise somewhere accessible. If something falls off in the New Mexico desert, you can drive a truck out and pick it up. If it falls off on the Antarctic ice sheet, it's gone forever.
Right. Good point. So it was a short flight.
Relatively short, yes, about 10 hours. The goal wasn't to do science, it was just to prove that the core systems work in that environment.
And how did it go? Did it, work?
But it was a classic engineering story, a mix. There were some absolutely spectacular successes and some really frustrating, but ultimately very illuminating failures.
Okay, let's start with the wins. What went right?
The biggest win, by far, was stability. You have to remember, this telescope isn't bolted to bedrock. It's a heavy instrument package, the gondola, hanging from a giant balloon on a long cable.
So it twists its ways.
It bobs in the stratospheric winds. It's a pendulum, a giant, multi-ton pendulum. And yet, the pointing system, the gondola itself, achieved what they call sub-arcsecond precision pointing.
Okay, break that down for me. What is an arcsecond in real terms?
Okay, so imagine a circle is 360 degrees. Each degree is split into 60 arc minutes. Each arc minute is split into 60 arc seconds. So an arc second is 1/3600th of a single degree.
That's a tiny, tiny sliver of the sky.
It's incredibly small. It's like the width of a human hair seen from about 60 feet away.
And they kept the telescope pointed that steadily.
They kept it steady within that tiny sliver while dangling from a balloon 25 miles up in the air. It's the equivalent of standing in one city and holding a laser pointer perfectly steady on a specific dime in another city miles away.
While you're hanging from a rope.
It proved that the stabilization technology, the reaction wheels, the star trackers, the control software, it all works flawlessly. That is a massive engineering hurdle to clear.
That's a huge win. What else worked?
The cryogenics. The cooling system for the infrared detectors worked perfectly. And that's essential because, remember, infrared is heat. The detector itself must be kept incredibly cold or its own sheet will blind it. So, 2 huge successes.
Okay, that's the good news. Now for the growing pains. The report mentions some failures, and I want to get into the details here because usually, these press releases just say successful test. They barely get into the nitty-gritty of what actually broke.
And that's what's so great about this report. They were very open about the failures, which is how science moves forward. First, a simple one. The GPS went down.
Even NASA has GPS issues. That makes me feel so much better about my phone's mapping app failing in the middle of a city.
It happens. High-altitude GPS can be tricky. But that was a minor glitch. The more fascinating failure, and the one that really teaches us about material science in extreme environments, was the aluminum housing for the telescope's bearings.
Okay, what happened there?
So the telescope needs to be able to tilt up and down. It's called changing its elevation. It has to do that to track the stars as they move across the sky.
Right.
The bearings that allow this smooth tilting motion, the joints, effectively were housed inside a casing made of aluminum.
Okay, aluminum seems pretty standard for aerospace stuff. It's light, it's strong.
It is. It's a great material for a lot of things, but at 40 kilometers up, the ambient temperature is brutal. We're talking around MEDIC of 60 degrees Celsius, maybe even lower. It's a deep freeze.
Colder than an Antarctic winter on the ground?
Much colder. And when metal gets that cold, it shrinks. It's called thermal contraction. But here is the crucial catch. Different metals shrink at different rates. That property is called the coefficient of thermal expansion.
I think I see where this is going.
The aluminum housing shrank more and shrank faster than the steel bearings that were housed inside it.
It crushed them.
Not crushed, but it clamped down on them. It's called a differential contraction. The housing, which should be a loose sleeve for the bearings, effectively became a powerful vice.
It squeezed them so tight they couldn't move.
It froze the mechanism solid. The telescope got stuck looking at one spot in the sky. It couldn't tilt. It couldn't track anything. The science part of the mission was a total failure because of this.
That sounds absolutely catastrophic. You launched this incredibly complex mission, and a simple, shrinking piece of metal ruins the whole thing.
On a real science mission, yes, it would be a complete disaster. If that had happened on the first day over Antarctica, the mission is over. You have a very expensive frozen telescope staring at nothing useful for weeks.
But this was the test flight.
Exactly. This is why we test. To an engineer, this failure isn't a disaster. It's a gift. It's a piece of priceless data.
How so?
Because now they know. They have the data. If they had skipped this test and gone straight to Antarctica, they would have lost the entire season, millions of dollars. Now they know, okay, the tolerance on that aluminum housing was wrong for these temperatures. The materials are incompatible. They can go back to the lab.
And fix it.
They can swap the aluminum for a material with a lower thermal coefficient that shrinks less, like titanium or a special alloy called Invar. Or they can simply redesign the housing with a slightly larger gap to account for the shrinkage they now know will happen.
So it's a cheap lesson learned in the New Mexico desert that saves a very expensive, very important mission in Antarctica.
Precisely. The report says the engineers are already hard at work fixing those thermal contraction issues. It's a completely solvable problem, but you only find it by actually going there and trying it.
So looking forward, we've done the test flight, we found the bugs, we've learned our lesson about shrinking aluminum. When is the main event? When does this thing fly for real?
The target, the big show, is the Antarctic summer of 2026-2027.
That's coming up pretty fast in the world of space missions.
It is, yeah. They are going to take the full flight-ready Excite apparatus down to the ice. And this time, they aren't aiming for a 10-hour joyride. They are aiming for a proper long-duration balloon flight.
How long is long in this context?
It can be weeks. The record for these kinds of scientific balloons is over 50 days. They'll be drifting in that polar vortex, circling the South Pole, just soaking up that continuous, uninterrupted starlight.
And if it works, if the bearings don't seize up this time, what is the potential scientific payoff here?
It's huge. The scientists on the project estimate that the single balloon flight, one mission, could double the total number of exoplanet phase curves known to humanity.
Double. With one flight.
Yeah. Double. Just think about that. Think about all the billions of dollars we've spent on all the space telescopes so far, all the decades of Hubble, the Spitzer Space Telescope, Kepler, now Webb. One balloon ride over Antarctica could equal the total historical output for this very specific, very important type of data.
That really puts into perspective how data-starved we are when it comes to really characterizing these atmospheres.
We are so data-starved. We have a good census of planets now, thanks to missions like Kepler and TESS. We know they're out there in their thousands, but we don't know what they're like.
Right.
We are just now moving from the era of pure discovery to the era of characterization.
It's the difference between knowing your neighbor exists because you see their car in the driveway and actually knowing what they cook for dinner or what music they listen to.
That's a perfect analogy, and Excite is the tool that kicks that door wide open for these hot Jupiters.
It really feels like a shift in mindset then.
Mm-hmm.
We aren't just looking for little dips in light anymore, for dots. We're looking for weather patterns. We are looking for wind.
And we're proving that you don't always need a flagship, multi-billion-dollar spacecraft to do flagship-quality science. Sometimes you just need a really big balloon, a clever location, and some very careful engineering.
I think that's a perfect place to wrap this up.
Yeah.
We've gone from the, common misconception that space requires rockets, all the way down to the physics of infrared light and the mechanics of a freezing aluminum bearing.
It's been quite a journey, from 40 kilometers up down to the micrometer level of a bearing contracting.
It really has. And I want to leave our listeners with one final thought that really stood out to me from all this. We usually draw a very hard line between atmospheric science, studying Earth's weather, and climate and astronomy studying space.
Right. They're totally separate disciplines. One looks down, one looks up. They are different departments at the university. They go to different conferences.
Exactly. But EXCITE just completely blurs that line. We are using the unique properties of our own upper atmosphere, its coldness, its dryness, its stable polar winds, as a tool to understand the atmosphere of a world that is hundreds of light years away.
We're standing on the roof of our own atmosphere to peek into theirs.
That's a beautiful way to put it. It shows that our planet isn't just a barrier to look through. It's an integral part of the observatory itself. It's a tool that we can use.
Our atmosphere becomes part of the solution, not just part of the problem.
So keep an eye on the news in late 2026. If you hear about a giant balloon launching from Antarctica, you'll know that it's not just checking the weather here, it's checking the forecast for a hot Jupiter.
Let's just hope they got the math right on that aluminum this time.
Fingers crossed. Thanks for listening, everyone. We'll catch you next time.